Hi, my name is Lambert Chao. I'm the Senior Technical Lead for Connected Devices.
My name is Markley. I'm also on the Connected Devices team at Wolfram Research.
We'd like to invite you to listen to our talk, How to Stream Data from Your Connected Device. In this talk, we'll show you how to acquire data from your device via polling and event models, how to build visualizations.
We'll also talk about data management and state management for graphical user interfaces.
What we're going to do here is this is, in a way, a little bit of a quick practical example. We're going to go for broad strokes here about how to stream data from any sort of device. And the device we'll show a couple examples, and we'll carry it through mostly from beginning to end. One of them will be how in a way, how current image might work. The other would be how an audio capture function might work. So first off, we'll talk about ways to get data into Mathematica. So there's a couple ways you could do it. You could poll for data, and we'll use the camera as an example. Or you could sort of do an event model, which will make use of these things called asynchronous tasks, which aren't very advertised. It's more of an internal function, but you'll get a peek at how that works. We'll try to dive a little into the low-level C code, just enough to give you an example of an idea of how you might do that. The idea is that you would sort of go off on your own and figure it out. We'll have a basic example to sort of get you started. And then I'll introduce a bit of an internal API of audio capture. And don't get too excited, it won't work on the builds you have. This is only on our internal code, but it's sort of a peek of what's coming for audio. And then so Caleb will take it over next and sort of carry you through from that API for capturing audio and put it together. There's a lot more to do. Even though you can get data in, you got to manage the data, you got to control the state of the stream, you got to visualize, you got to have a GUI. Now, if you want more detail, technical detail, I suggest you take a look at our tech conference talk from last year, how to connect your device to the Wolfram language. And it's actually online in a screencast with notebooks and production and sample code that'll run on all platforms. So take a close look there. So but any of the technical low-level stuff, you're going, oh, he's glossing over all that. Look here, I'll set up. In fact, I used some of the code we got from there as well. Alrighty. So let's start off, just jump right in. So here we're going to talk about the polling model, where you keep asking repeatedly for new data. To do that, you got to be able to start gathering one data point. We're going to use the camera. And so we're just going to, this is more stuff to, so you see it works, nothing up our sleeves, but you're less interested in exactly what's happening here, broad strokes only. So this is using OpenCV, the JLink wrapper version, the Java wrapper. And so we're using some JLink code here. It's sitting in this particular location on my computer. And this is actually available from, if you go to that link I just showed you. So then I create an open camera function that's really just to initialize things. You see there's nothing glamorous here. I'm loading some class paths so I can get to this Java class loaded. I set some, some widths and heights and so forth. Then we need our core function, the grab frame. So we just do camera capture. It gives us back an array of data, and we wrap it in an image. And put it in RGB space. So open camera. The light comes on in front of me here. You guys can't see that. And there we go, grab frame. So we have an image working. That's the first step. We have one image. So now we go to, whoops. I don't know why I hit that button. Now we go towards more of the, and are we there yet model? That kid in the back of your, backseat of your car going, are we there yet? Are we there yet? Are we there yet? So you keep asking for data. And there's a function called schedule task in Mathematica, so you can run schedule tasks here. And basically it says, this expert just keeps it getting evaluated in various models. What we'll choose to do is we'll keep evaluating it 12 times a second. So basically I start my camera stream here. And it's as simple as, my single frame, I grab it, and I store it in a $ current image variable. And, comma, how many times a second, or, how often it repeats? Well, I want it to repeat 1/12 of a second. define my start stream function. And then there's an API for removing the task so you don't keep going. And I want to clean up after myself, so I close the Java code, the Java instance or whatever. So define my stop function. And now I can start the stream. And visualizing is as simple as putting $ current image in a dynamic. There we go. Okay, so then you stop the stream, and as simple as that. So that, in a gist, is sort of how current image could work. And so it's as simple as if you can write some code that's the graph frame function, no matter what device you want, an instrument or an Arduino or something, you can easily use a polling model and run scheduled tasks to sort of start looping through and getting data for you. So that's pretty straightforward and pretty natural. Sort of just ask for it when you want it, and you start caring about how often you get it and how reliable that is. So that's one way to do it. It's a little tedious, and it really depends on your ability to, if you care about how often the data comes back in a reliable periodic manner, it really depends on the ability to, if you keep Mathematica busy, it might be stuck doing an integrate, it might not ask for the data at the right time. It might be a little off. Do you care about that jitter? So now there's a thing called, there's this model called an event model, which is sort of said, wouldn't it be nice if, say, it's about trust, right? So I say, I know these events are going to happen. Data could arrive, or the camera could break, or something else, And I set up an event in advance. I have somebody I trust, and I say, well, if and when event A happens, data arrives, then evaluate this callback function. It's called a callback function because you think of it as you're diving into the low-level code. You're stuck in there in some thread handling, all the data coming at you. And every time you have a data, you call back into Mathematica and say, here's the data. Okay, so this is a bit of, some of you may be familiar with this, but for some of you, this might be a less familiar paradigm for programming because you're so used to procedural. You don't know when it's going to happen. Basically, you have somebody you trust, and I say, hey, Caleb, when this happens, can you just hand it to me in an appropriate container, and I'll deal with it. And then you can set up, these are called events, and you can set up a few of them. So it's about designating a callback function. So how do we do that in Mathematica? Well, as alluded to before, there's a asynchronous task API. So asynchronous means it doesn't block, right? It's happening in the background, and it raises what's called an event in the callback function, and I'll deal with it when I can. But it doesn't block my ability in the background to keep handling the data. Whereas if I'm polling, whatever I'm doing, it's blocking me, and I can't do the next thing. So that's what's called asynchronous. Not synchronous as in blocking, but asynchronous. So just roughly, we'll go into exact details here, but we'll have a create asynchronous task function. You don't have to worry too much about it. Basically, it's wrapping a low-level library link C function. We'll show you an example. You throw in some arguments that you might want to give it to set up, and then you register a callback function. This callback function is a Mathematica function that gets evaluated whenever data comes back. And it returns an asynchronous task object, and of course you have functions to start, stop, and remove it. So let's dive in here. Just some unglamorous setup here, but let's look a bit at the C code. So we'll just look at the important functions here. You can look at the other talks to see how to deal with library link. But basically, you start your simulated input stream. It's like open camera. You do some preambling. You get some data from Mathematica. Here, I'm interested in the dimensions of the data I want, which is the sampling rate, how often, how frequently my data comes back, and sort of how many samples I have. But the core of it is I have to tell Mathematica I want to create an asynchronous task with thread, which means if you guys are familiar with C thread coding, I don't have to deal with pre-threads or something. Mathematica will take care of that, the C code part of Mathematica. All I do is register what's called this callback function, push simulated data, which I'll show you in a sec, and then arguments that it may need. Yeah. The callback function is pretty straightforward, but it's also where everything happens. So it's just something that once you launch the thread, it just keeps running in the background in this while loop while this asynchronous task is alive. So as long as I have not called remove asynchronous task, this will keep going. And all you do is nothing simple. It's pretty straightforward. You just create an M tensor, which is a mathematical container for an array. And then I just fill it with random data in the for loop. And then I create what's called a data store. That's the asynchronous task data container to serve it back to Mathematica. I add in that M tensor I created, so that's my payload. And then I raise the async events, and I throw it back into Mathematica. And once Mathematica gets it, it will call that top-level callback function where I can do fancy stuff, and you'll see what happens there. So I'm not going to go through this, but you can use, if you're familiar with the C compiler driver, you can just create this, compile and create this binary in Mathematica. I've already done that here. So that's sort of the low-level stuff. How do you put it all together? I load the library functions, nothing glamorous here. And then basically, all it's telling me is it's in this library, C library, and this is the function, just that C function I wanted to load, some arguments, which was just the dimensions and the frequency, and then what I'm expecting back, which is an ID number for the asynchronous task. But you see it changed the callback function there, and that's done using store current data. And then, so you see when I actually create the asynchronous task, I start the simulated input stream, which is a Mathematica library function now that's wrapping the C function. My arguments are here, and store current data is my callback function, which all it did was take the payload event data and put it in the $ current data value. So now you can see, before there was nothing, no asynchronous tasks. I create the asynchronous tasks. There's one there. And I can start a dynamic, and that just shows me a list line plot of the random data coming back. So this is random data generated in the C code. Nothing exciting here, but this gives you an idea what happens next when we go to the audio capture code. Of course, I can stop it, I can restart it, I can remove it, and once I remove it, there are no asynchronous tasks left. Okay, so capturing audio. Now, this is sort of wrapped as internal code, but basically it's pretty much the same thing. Instead of the random number generator, I'm calling the operating system. We use AudioCube OS X API to grab data. So first off, I find my built-in microphone. I create a similar asynchronous task with the input device I want. I designate my callback function, which just says store it in the variable current audio, the raw data. And here's my dynamic, no data to bring back, but once I hit start, focus, you see this is the live stream of audio data that's being captured and coming back to me. So now we can go ahead and stop it, remove it, and so forth, but this gets us in the ballpark. And so there's a lot more to do, but data is just coming back at you, but you gotta be able to handle it and deal with it, control it. So Caleb will start next and show you how to, various states to take it from this raw API, you could sort of say it's a given to you, and then go into creating what looks like the audio GUI that you see in the new functionality we built.
Hello, test. All right. Thanks, Lambert. All right, so now that we've gone through all that, now what? What do you do when you have access to the data from your device? There's obviously any number of different things you could do, but we'll be focusing on some common ones. Data management, functionality and design, state management, and visualization. Throughout the rest of this talk, we'll be looking at specific ways to implement these things, and we'll be focusing on fairly straightforward approaches. You'll probably see redundancies and other opportunities for optimization, but those are included for the sake of clarity. So let's look at data storage first. Here are 3 straightforward approaches to data storage in the Wolfram language. One is appending elements to a list. One is adding key value pairs to an association. And then finally, editing a pre-allocated buffer, which in this case is also a list. The idea here is we're streaming data constantly. So we want to be adding data to our chosen container also continuously. So let's look at each option. The first option is using a list and append to. This is probably the simplest option and the most familiar. It's easily growable, and we can check out the performance here. I've got my data, and I'm just appending that data to a list. It seems reasonable, at least at first glance. So let's take a look at association next. If you're not familiar with association in the Wolfram language, it's essentially a map. Each element contains a key, which then maps to a value. This is also easily growable, but one thing to take note of here is that the performance is considerably better. So finally, we have a pre-allocated buffer. We initialize a list with zeros and then simply change those values as we go. So this is actually going to be the fastest method, as you might expect, but not that much faster than association. This implementation, however, is not growable. If you were to use one if you were to modify this into, say, like a ring buffer, it certainly could be growable, but in that case, it adds additional complexity that you may or may not want to deal with. So you'll have to decide for yourself which of these or any other method makes the most sense for your purposes. For our purposes, streaming audio data as it's happening is performance sensitive, so we probably want to avoid just appending to a list. Since the association buffer options have similar performance, we'll go with the simpler approach for this talk. Additionally, it also has the added benefit of making individual buffers of data more easily accessible for our visualizations. So next, we're going to talk about, we've talked about data management. So we're talking about our actual data management symbols. So we've decided on our storage method. Let's figure out what we need to keep track of. Audio input data will be our association that's used to store the audio data. When we have data to store, we'll add it to audio input data using associate to with audio index as the key. When we finish streaming our data, we'll consolidate our data and store that in the symbol audio data. Again, we're keeping it pretty simple here. So let's look at one of the actual functions we're going to use to build this structure. This is our reset function. All we're doing is taking our data management variables, initializing them, as well as setting the audio task to none. So for clarity, data management related symbols will be highlighted in pink, and streaming related symbols will be highlighted in blue. Those will probably look familiar from Lambert's previous slides. So let's talk about functionality and design next. Let's talk about our goals. We want to record live audio. We want to visualize live audio during recording. We want to be able to pause the recording, and we also want to stop the recording and consolidate our recorded data. So let's go ahead and take a look at the finished product here before we continue to dive through the implementation. So you can see we have an area in the GUI for the visualization, a button for starting the audio recording. You can also press that to pause it. We can record some more, and then finally we can press stop to finish and then export to $audio data. We can then do something, so we know our data is now in audio data. We could create an audio object. We want to rescale our data. A button for starting the audio recording. Oops. And then we have that. Yeah, so this talk isn't focused on GUI particulars. There's a lot of other good talks happening today and tomorrow on that. But we'll go through what we have here, mainly for the purposes of state management, visualization, and as well as data management. Okay, so we'll talk about state management next. If you're not familiar with the concept of state, it's essentially a certain configuration of values that information in our case, Wolfram language symbols have at a given time. So at any given time, we could be recording audio, we could have recording paused, or we could not be recording at all, which will be our stopped state. So we've got two symbols here, started, which will be true when recording or when paused. And then we also have, and it is false when recording is stopped. We also have the symbol recording, which is true when recording, false when paused or stopped. So our three states, we have recording when both are true, paused when recording is then false, and then stopped when they're both false. If we are able to reach some state where started is false and recording is true, we're going to have some problems. So this is our initialization function. We've talked about our state. Let's get that set up. So first, we've got our stream-related symbols. We have device, which will be the built-in microphone found via audio device discover. We set our sample rate, our samples, which are the number of samples we're capturing in each buffer. Next, we have the callback function. This looks a little bit similar to one of Lambert's previous slides, the callback for current image. So in this case, it's pretty simple. We associate the data accessible by the callback through this data parameter here. We associate that to audio input data using the key audio index, and then we increment audio index. Yeah, so pretty straightforward. Then we have our state. We have started recording. We initialize those both to false, and those state-related variables are going to be highlighted in green. Finally, we have some other symbols at the bottom in gray text. They're related to visualization and graphical assets for the GUI. Those are going to be highly dependent on your design choices. They aren't strictly relevant for this talk, so we don't really spend much time talking about those when you see gray text. Okay, so we've gone through our data and state management symbols. Let's start diving into the rest of the code to make this, this GUI. So live audio is, capture audio is a top-level user-facing function we saw before. It calls our initialization function, and then it calls GUI, which is below. The GUI function is simply a grid. The first row contains the visualization. The second row contains a dynamic of our record function. The only argument there is our recording, our state variable recording, and then also stop. So next, let's go ahead and look at record, stop, and viz. So we'll start with record. The argument we pass in from GUI is recording. So for this down value used, this is when we have not started recording yet. Record is just a button. Its label is a graphic asset. When pressed, if we're starting a new recording, we'll call reset to reset our data management variables. We'll then create a new asynchronous task with our stream-related symbols defined in the initialization function. So all these should look familiar, and you'll recognize run. So this run audio capture asynchronous task is an internal function similar to what Lambert showed before, where you start your asynchronous task. So this will begin streaming data from the microphone, and each time that our callback, which we've passed in as a parameter here, every time that is called, it will store the data. We then set both recording and started to true, and we can see, if we just put a frame around that, what this is. So next, let's look at our pausing the recording. So this is our down value for when we've already started recording. When the button is pressed, we stop streaming of data by stopping and removing the asynchronous task. We'll also go ahead and clear our audio task just to be safe. And then finally, our state needs to be set to pause. Started is already true, so we just set recording to false. We've got this guy as well. So finally, we'll talk about stop. When stop is pressed, we want to stop streaming. You'll see this is very similar to the pause button. We also want to clear our audio task. Let's see. And since we're, okay, so we also want to consolidate our data for use, say, in an audio object or something like that. So we'll go ahead and combine all our recorded audio data together and store it in audio data. And since we're back to our stop state, we set recording and started to false. All right. So the last thing to cover here is the visualization. As stated before, it's obviously going to be dependent on what your goals are and what data you're collecting. For example, when Lambert was showing current image, the visualization was just dynamic of current image. However, we'll go ahead and go through how we're visualizing the audio data in this GUI to give an example of a way to use each buffer of stream data individually as opposed to using it all at once, like when we're creating an audio object from that captured data. Okay, so if we are currently recording, we want to grab the previously recorded data buffer from audio input data. If we're not recording or if there's some error accessing that data in audio input data, we'll just use an array of zeros or a list of zeros to give a flat line in the visualization. So once we have our data, we turn that into data points that can be usable by a graphics object, which will then draw that waveform. So we've gone through pretty much all we needed to create that audio capture audio. And you want to do the conclusion?
Yeah.
Okay.
Do you want to show the payoff again?
Oh yeah, sure.
While he's showing that, yeah. So basically, you've seen a couple ways, models of how to get data. Again, to remind you, polling or event-wise, and then you see sort of how we can deal with it, how we can manage it, and so forth. If you go to the next slide, please. And then so, remind you again, scheduled tasks and asynchronous tasks for you to deal with it. And then now hopefully you can sort of take this basic caricature and sort of apply it to your device. So I remind you to take a look at our talk from last year if you wanted more technical details. Finally, some interesting talks I wanted to make sure you guys are aware of. We have 3 audio talks tomorrow related to this. And also come down to the connected devices playground, and we have a bunch of these things set up, and we can talk in more depth, and you can play with some of the stuff we have in sort of skunkworks mode. Yes?
I noticed in the beginning where you loaded the buffer, the fixed buffer,
Mm-hmm.
you just had an index incrementing, but what kept it from running off the end of that?
You mean what Caleb did?
Yeah.
Well, it's a growable container, right? The asynchronous task. So are you talking about a fixed buffer?
Yeah, the fixed buffer for that particular example, we have a fixed size that's for like an example where you know exactly how much data you're going to read, and you're not going to need any more than that.
Right.
If you're going to do something else.
Just an index plus plus, it didn't have any limit. So what kept it from just running
Right. So his case actually was not exactly what we were talking about here. So suppose you did audio capture of 3 seconds. You know how big it is, but it's coming back to you half-second increments. But that's where it gets challenging, right? Because when he was talking about ring buffer, that means you can mod it and sort of loop it back, but then you lose data when you loop back, and it becomes a bit of a hassle. But yeah, so so a few ways to deal with it. Yes. Yeah, well, that's a very good question. So we do a lot of that in C code, like, in a way, a lot of the heavy lifting was done in that library link stuff. There you have, C mutexes. Mathematica, if you're familiar, it's a single evaluator, and it's cooperatively preemptive, right? So basically, you'll be doing, say, an ND-solve, and then you'll preempt and say, hey, I want to deal with this data that's coming in. So there's a function called preempt protect. And what you try to do is sort of anything where you're accessing something you would want to mutex up, you try to use preempt protect to think of it loosely as trying to make that operation a bit atomic, say. Yeah, preempt protect. You want to be careful when you use it. It's a bit of a heavy dynamic, sort of a high wire balancing act. So sometimes you could easily lock things up. So that's where a lot of the challenge can be. Yes?
Why was the association store so much faster than the list?
The list is, so basically a list it turns it into an expression in Mathematica, and it's a very heavy struct. There's a lot of metadata around it. So every time you append to, you're actually recopying all the stuff there, and expanding it every time you're generating a new expression, so it doesn't scale well. So you keep growing it. And the association is sort of more designed to be, growable and insertable. So.
Is there any advantage to how lists are implemented?
Sure, you could throw, ints with symbols, with whatever. It's more geared towards symbolic. But we're dealing with high performance data management. So, yeah. Yes.
What would be a quick and dirty kind of way to implement like an alert for the camera case? Like you wanted to monitor like a hallway?
Sure, yeah. So in the dynamic of $current image, you could have a function there that sort of does image processing and then does a sentinel or something. Or if you were doing the asynchronous task one where I had the callback function, there you can sort of hook it into your callback function. And the second one is a bit more, it doesn't require dynamics, so the evaluator has a bit more time. Dynamic, again, is sort of more performance demanding, also requires that the dynamic be visible otherwise it doesn't update. It's trying to conserve power. Okay. Chris, do we have a next speaker in here? Okay, yeah, I think we should wrap up. Please feel free to find us after the talk.